So now I'm going to erase is greater or equal to, because of infinite convergence theorem, and this is alpha bar equal to alpha star. And now we are ready to prove another lemma. 3. So let Cik equal to C of Z1 Ik, etc., Zn Ik. This sequence, okay, infinite sequence of nested cones obtained via the algorithm. So lemma 1 Zi Zj Zjik, they all converges to some Z star with K, and this is J equal 1 till N. Okay. Now, this theorem says that delta of Z star is optimal. Okay. So the proof, so we go to the same picture as we have before. So remember in lemma 2, we showed that VQ was the optimizer of the LP and V bar Q. Just refer back to the lemma 2, and V bar Q converges to over Q to delta of Z star. All right, and gamma Q converges to, for Q converges to 1. Gamma Q is the optimal value of that linear program. And here, of course, I'm replacing Ik by Q to simplify the notations. Now, so V bar Q, as in lemma 1, we said it belongs to the convex hull of the Y. So this is equal to the sum of I equal 1 till N of lambda IQ, YIQ, and E transpose lambda Q equal to 1, lambda Q greater or equal to 0, right? Just as we did in lemma 1, which is equal to the sum of lambda IQ, theta IQ, times delta of ZIQ, right? I equal 1 till N, right? So V bar Q converges, right? So everything here converges. So converges subsequentially. So it converges to the sum of lambda I, theta I, times delta of Z star. And here E transpose lambda equal to 1, lambda greater or equal to 0. So, and here we have V bar Q converging to this. All right. So therefore, sum of lambda I, theta I, that's equal to 1. I equal 1 till N. Remember, the theta IQ are greater or equal to 1. So this theta I, so here E transpose lambda is equal to 1, lambda greater or equal to 0, and the theta i's are all greater or equal to 1. So therefore, for all the lambda I that are positive, we must have theta I equal to 1. So there exists an I such that lambda I star is strictly positive, right? Because E transpose lambda equal to 1. One of them has to be positive. And because it's positive, that means theta I star is equal to 1. It has to equal 1. And therefore, yiq, right, converges to, which is equal to theta iq delta of ziq, right? This converges to theta I star, let's call it I star here, converges to theta I star times delta of z star. All right. So therefore, and theta I star is equal to 1. So this is equal to delta of z star. But so this specific y converges to delta of z star. But what do we have? We have alpha bar q is equal to f of yi star q, right? By construction of the y's. And this converges to alpha bar q converges to alpha star, right? And the y converges to the delta z star. So this is equal to f of delta of z star. And therefore, delta of z star is optimal. Let me add a couple of assumptions to the list of assumptions we have. What I'm going to assume is that if x star, we denoted x star by the optimal solution of this program, then x star is a vertex of this region, and also it's a strict local minimum. In other words, in the neighborhood of x star, f takes on a bigger value. Okay, so x star is really the optimal in the area. Okay, and the next assumption is I'm going to assume that f, our function f, is continuously differentiable around x star. Okay, so we need these two assumptions to prove finite convergence. So the next lemma, let's call this lemma 4. Let Cik, same thing, Cik defined by the vectors z1 ik, etc., zn ik. This sequence here, an infinite sequence. Nested cones obtained via the algorithm. So from the previous result, right? From the previous result, we know that ziq, ziik converges to z star, and also delta of z star is optimal. That's from the previous theorems. Now, no, delta of z star, this is the lemma, delta of z star is the unique optimizer of the linear program minimize the gradient at delta of z star times x subject to ax less or equal to b, x greater or equal to 0. Okay. So this is the notation. This is the gradient. We are assuming differentiability. So the gradient at delta z star exists, and delta z star will be the unique optimizer of this linear program. And the proof. So let y such that ay less or equal to b, y greater or equal to 0. Right? Any point, any feasible point. And assume that delta, the gradient of delta of z star y is less or equal to the gradient of f of delta z star times delta of z star. Okay. That delta z star is not the unique, so there is a y such that this. So now if we let x of lambda equal to lambda y plus 1 minus lambda delta of z star, okay, a linear combination, and lambda, your lambda between 1 and 0, x of lambda. So this is y is feasible and delta z star is feasible. So this is a feasible point. In other words, a of x of lambda is less or equal to b, and x of lambda is greater or equal to 0. Then if I do delta of f of delta z star times x of lambda minus delta of z star, that's equal to, so I plug in here x lambda. So this is just delta, that's just lambda times delta f of little delta of z star times y minus delta of z star okay, and now lambda is greater or equal to 0, so this is less or equal to 0 for every lambda between 0 and 1. So I could make lambda close to 0, all right? So x lambda will be in the neighborhood of delta z star, okay? And I have this. And remember that concavity implies pseudo-concavity. Right? So this implies that f of x lambda is less or equal to f of delta of z star. Okay? From here to here is just pseudo-concavity. All right? Since this is less or equal to 0, then the function follows. Okay? And this is where the contradiction occurs. Right? Because delta of z star is optimal, right? So therefore it must be a vertex and a strict local minimum. And here I found a point that's less or equal to that, a feasible point. That's a contradiction. So therefore, this assumption here is false. This is false. Any point in in ax less or equal to b, x greater to 0, the delta has to be bigger than at delta of z star. The consequences of this lemma 4 is that since x equal to 0 is feasible, remember, b greater, if you plug x equal to 0, it satisfies this. So if you plug 0 there, then I'll get delta f, the gradient at delta of z star times 0. That's strictly bigger than the gradient at delta of z star times delta of z star, because delta of z star is a unique optimum. So therefore, and this is equal to 0. So delta, the gradient at delta of z star times delta of z star is strictly negative. So, and this leads us to the next lemma, which I call lemma 5. The same assumptions, and here I'm just going to put this, that the result we got, the gradient at delta of z star times delta of z star is negative. Okay? And then I erase all this. Okay. So we have an infinite sequence of nested cones, which means all this. Then the result is that yiq, yiik, y of j ik converges as k goes to infinity to delta of z star for j equal 1 till n. Remember, in the previous lemma, we showed that at least one of them have this. But now, with these new assumptions, all of them must converge to the same point. Just like the z's converges to z star, the y's will all converge to delta of z star. Okay. Let's here also ik is just q. Okay. So yiq is equal to theta iq times delta of ziq. And this converges as q goes to infinity to theta I delta of z star. Okay? We've seen this before, where theta I is greater or equal to 1. And f of yiq is equal to alpha bar q converges to alpha star. So therefore, f of theta I delta of z star is equal to alpha star. All right, now because delta f of delta star, delta of z star times delta of z star is negative, this implies that f of gamma delta z star is strictly less than alpha star for gamma greater or equal to 1, for gamma bigger than 1. All right. So this is delta z star is a descent direction. So any point beyond delta z star, we get less than delta z star. So therefore, this and this, therefore theta I must equal 1 with this and this. Okay, and therefore putting in theta I equal to 1, then I here prove that y of iq converges to delta star. So that here I'm going to make the connection to the non-degeneracy property that I introduced. So let's assume that, and I call this the fundamental theorem because this is the key theorem to the finite convergence. So let's assume that we have a sequence of cones, okay, and these cones are obtained using the exhaustive non-degenerate subdivision process. The exhaustiveness implies ziq converges to z star. And we're going to assume that our function is continuously differentiable around the vector v star, and the gradient at v star times v star is not zero. Okay, and then I have this point that I call yiq, which is equal to theta iq ziq, and all these points converges to the same point v star. So I equal 1 till n. Now, if we form the matrix similar to the matrix that we did with the simplices that defines the cone, so it's a directional. So here's y1, y2, y3. So I have a matrix that has this directional. So it's yiq minus yjq over the norm for I strictly less than j. So because this is an n-dimensional, an n minus 1, this is an n-dimensional cone, then the rank of SQ is n minus 1. Okay? Like here, I am in n equal to 3 here. I'm in 3 dimension. These directions are of rank 2. Then, since SQ, the norm is equal to 1 of all the columns, then SQ converges subsequentially. So here, I'm putting SQ converges to S, subsequentially if necessary. Okay. Then the theorem says, same thing as non-degenerate definition, the rank of S is n minus 1. Okay. And remember, non-degeneracy we have this matrix which we call DQ, which is ZIQ minus ZJQ over the norm of ZIQ minus ZJQ, I strictly less than J. Non-degeneracy says that DQ converges to D, and rank of D is equal to n minus 1. Okay, for the simplex defining the n minus simplex defining the cone, the directional converges to n minus 1. So this property here, that's the non-degeneracy property, extend to the y vectors. Okay, when all the vectors converge to v star. So now the proof of this fundamental theorem is very lengthy and tedious. So I'm not going to go through it in this video. But here's where you could find the detailed proof, either in my paper, M. Hamami and Stephen Jacobson, in Mathematics of Operational Research, Volume 13, Number 3, or you could go to see the book by Horst and Tuy called Global Optimization. Okay, and they have a section. They have a section in that book that talks about my work, and they also include the proof of this theorem, of this fundamental theorem. Let's prove this important theorem. So again, we have a sequence of cones. It's an infinite sequence of nested cones obtained via the exhaustive non-degenerate subdivision process. The exhaustiveness implies ZIQ converge to the same vector Z star. And in the previous result, we showed that delta Z star is optimal, and the gradient at delta Z star sum delta Z star is strictly negative, so it's not 0. And the alpha extension of the y's all converge to the same vectors. Okay, so we have all the conditions of the fundamental theorem. So therefore, the matrix SQ equal to yiq minus yjq over the norm I strictly less than j. This converges subsequentially, if necessary, to a matrix S such that the rank of S is n minus 1. Okay, that's the previous fundamental theorem. Okay, now what this theorem says is, remember the LP that we solve at every iteration is maximum E transpose h cubed minus 1x subject to x belonging to the cone and feasible. Well, if we take the norm of that vector, divide by the norm, so normalize it to 1, that converges to minus the norm of the normalized gradient of the function of delta of z star. So geometrically, what does it mean? So here I am in 3 dimensions, okay? And I have my f of x equal to the optimal value, okay? So that defines a surface in 3 dimensions. So here, the surface, I'm assuming it is a circle. It's a sphere, okay? So here's my cones, z1, z2, z3. So this cone is going to collapse to a single ray. And this is the alpha extension, the y's, okay? So therefore this plane here is the Tuy plane, okay? What does this say? This says that in the limit, this plane here is going to converge to the tangent hyperplane to this surface, okay? Because the gradient is a vector perpendicular to the tangent hyperplane. So that's what these results say. So let's prove this. Now, we have f of y. Since f is continuously differentiable around delta of z star, then we could write f of y iq is equal to f of y jq plus the gradient of f at y jq times y iq minus y jq, right? Plus something insignificant compared to the norm of y iq minus y jq, okay? This is just the first terms of the Taylor series, okay? But remember, Fyiq is equal to Fyjq. They both equal to alpha bar q, okay? So that cancels out, and then if we divide by the norm, then I get delta f of yjq right, times yiq minus yjq, and then I normalize this, divide by the norm, all right? So these are equal, it cancels out, and then I divide both sides by the norm, and this one divided by the norms converge to 0. So this thing here converges to, first of all, it converges to 0, right? And okay, so therefore, this delta of yjq, remember yjq converges to delta z star. So this implies that delta f of delta of z star, right, times, and this converges to the matrix SS times S, that's equal to 0. All right? So that's one result. Now, how about E transpose? E transpose HQ minus 1 YIQ is equal to E transpose HQ minus 1 times YJQ, right? And that's equal to 1 by construction of the Tuy plane. So therefore, E transpose HQ minus 1, then I'm going to normalize it, times YIQ minus YJQ, right? This is equal to 0. right? And therefore, if I divide by a norm, it's still equal to 0. So therefore, E transpose HQ minus 1 over the norm of E transpose HQ minus 1 times SQ, the directional matrix of this, that's always equal to 0 for every Q. And therefore, if we take the limit, then E transpose so therefore, the limit of E transpose HQ minus 1 over the norm E transpose HQ minus 1, so the limit of this over Q times S, that's equal to 0. Okay? So here, but rank of S is n minus 1. From the fundamental theorem. So here you have two vectors, this vector and this vector, that are both perpendicular to a matrix that has rank n minus 1. And therefore these two vectors are proportional to each other. Okay? So delta, the limit of E transpose HQ minus 1 over the norm E transpose HQ minus 1 over Q, this is some lambda times this vector here, delta F of delta of Z star. Okay? So if I normalize this vector, we know delta of Z star is not 0. Right? So if I normalize this, then this becomes just a plus or minus. Okay? And now, why is it minus? Because delta F of delta of Z star times delta of Z star is negative, right? We know that. And E transpose DQ minus 1 times YIQ, that's equal to 1. That's strictly positive. So the limit, so if I now if I do E transpose DQ minus 1 over the norm of E transpose DQ, this is HQ minus 1, sorry. I called it HQ minus 1. So E transpose HQ minus 1 over the norm of E transpose HQ minus 1 times YIQ, that's greater or equal to 0. All right? So therefore, if I take the limit of this times this is delta Z star is greater or equal to 0, and this is negative. So so here the minus is the correct sign. Okay. So this is a crucial theorem, is that the Tuy plane, because of the property that introduced the non-degeneracy of subdivision processes, under some mild conditions, the Tuy plane for any infinite sequence will converge to the tangent hyperplane. Now, lemma 6. Let CQ equal to C of Z1Q, etc., ZNQ, an infinite sequence of nested cones obtained via the algorithm, then we know the following. We know that ZIQ converges to Z star over Q, I equal 1 till n, right? We know also that delta Z star optimal vertex, all right? And we also know that delta, the gradient of F at delta Z star is negative. And we also know that the limit, that the E transpose HQ minus 1 X, E transpose HQ minus 1 X normalized converges over Q to the gradient, to minus the gradient at delta Z star over normalized delta F of delta of Z star. Okay, we know that. And this is, of course, subsequentially, if necessary. We know all this. So the theorem states that for infinitely many Qs, for infinitely many Qs, the delta Z star is the unique optimizer of maximum of our linear program, E transpose HQ minus 1 X subject to AX less or equal to B, X belonging to CQ. Okay, so for infinitely many Qs, delta Z star will be the unique optimizer of this LP. Okay, now let's prove this. From lemma 6, we know that delta of Z star is the unique optimizer the following: minimize delta F of delta Z star X times X subject to AX less or equal to B, X greater or equal to 0. From lemma 6, we just proved this. Okay, now this program here is equivalent to maximize minus delta F of delta of Z star over the norm delta F of delta of Z star times X subject to AX less or equal to B, X greater or equal to 0. Okay? All I did from here to here, I divided by a constant, delta F of Z star, and instead of the min, I did maximum or minus. So the two programs are equivalent. So delta Z star is the unique optimizer of this LP. All right? But for this vector here converges subsequentially to this vector here. And because AX, such that AX less or equal to B, X greater or equal to 0, finite set of vertices, right, it's a bounded polyhedral set. So here's the convex hull of its vertices. Then, and because this converges to this, then I can say that that delta of Z star is the unique optimizer of maximize E transpose HQ minus 1 over the norm of E transpose HQ minus 1 times X subject to AX less or equal to B, X greater or equal to 0. And here, of course, subsequentially if necessary, right, on Q. Right. Because this vector converges to this vector, and the fact that the polyhedral set has a finite set of vertices, this is a trivial consequence of that. And therefore, this implies that delta of Z star is the unique optimizer of maximize E transpose HQ minus 1 X subject to AX less or equal to B, X belonging to CQ. Right. From this program, we can get rid of this constant on the denominator. It's the same thing. And then this set here is contained in this set. So this is an obvious result of that. Therefore, here and here, of course, subsequentially, if necessary. So therefore, for infinitely many Qs, delta Z star is the unique optimizer of the LP at iteration Q. Okay, so now we are ready for the big theorem of finite convergence. So theorem 5, and this is finite convergence. The exhaustive non-degenerate conical algorithm converges in a finite number of iterations. So we're not relying on epsilon optimality. After a finite number of iterations, we have the exact optimizer of this program, the exact x such that it produces as the minimum of our objective function f of x. So what does this mean? It means that there is a q star such that m q star is empty. Remember MQ. MQ is at each iteration is a set of cone that needs to be searched. At some iteration, it's going to be empty. We have no longer any cone to search. So, in other words, and this of course implies that f of x bar q is equal to alpha star, the optimal solution. So x bar q star. So the x bar that we have, the best solution at hand at iteration q, that is the optimal answer to this problem. Okay, so the proof, we're going to do it by contradiction. Assume the algorithm is infinite. Okay. Therefore, if it's infinite, at every iteration we have a cone to be searched. So if we look to the tree, we're going to find an infinite sequence of nested cone. So let CQ infinite sequence of nested cones. Okay? So therefore, all our lemmas and theorem that we have done so far, the result holds valid. And especially the last one, which is for infinitely many Qs, the delta Z star is the optimal, is the unique optimizer of the LP. So in here, so we have ZIQ converging to some Z star, okay, and delta Z star optimal, unique optimize, optimal vertex of our set, right? And also it's a unique optimizer of the LP, that is maximum E transpose HQ minus 1 X subject to AX less or equal to B, X belonging to CQ. All right. And unique, this is subsequentially if necessary. All right. In other words, it may not be valid for every Q, but for infinitely many Qs it's valid. So let Q star, the first index, all right, such that delta Z star unique optimizer of the LP, right? Of that LP, this LP over here. Now, since delta of Z star is a vertex of our feasible region, optimal vertex of this feasible region, and if we look to the definition of the algorithm, CQ star is subdivided along delta of Z star, right? Remember when the optimizer is a vertex, we split the cone along that vertex. If it's not, we'll use the exhaustive non-degenerate process to subdivide the cone. And therefore, delta of Z star is an extreme ray of the next cone obtained from this, that is Q star plus 1. Okay? It becomes an extreme ray of the cone, that delta, the delta of Z star. So now, since this is for infinitely many Qs, delta of Z star is a unique optimizer of this, then there is a Q bigger than Q star, right? Such that delta of Z star unique optimizer of the LP of the following LP. I wouldn't say iteration Q, but it might not be iteration Q. So maximize E transpose HQ minus 1 X subject to AX less or equal to B, X belonging to CQ. all right? Because we have infinitely often delta of z star is a unique optimizer of this. So for iteration after q star, I'm going to find q bigger than q such that delta of z star is the unique optimizer of the LP. Okay. But CQ is inside CQ star plus 1, right? And therefore delta of Z star is an extreme ray of CQ, right? Because it's an extreme ray of CQ plus 1, and CQ is contained on CQ plus 1. And therefore, by construction of the algorithm, remember that the y's are always above the extreme ray, delta of Z star. So therefore, E transpose HQ minus 1 times delta of Z star is less or equal to 1. Delta of Z star is under the y, right? So therefore, this is less or equal to 1, contradiction. Right? Because the sequence is infinite. That means that the value of this is bigger than 1. And here we showed that it's less than 1. Okay? And therefore, the algorithm converges in a finite number of iterations. Now, so that concludes the proof of finite convergence. So now, let's go over all the assumptions we have made all along when we did the proof and see which constraints are really strong, which constraints are weak, so that we can extend the set of problems that can be solved by this conical algorithm. Okay, so the first thing is feasible set is bounded. So we assume that the set of x such that ax less or equal to b, x greater or equal to 0, we assume that's bounded. Well, in a practical situation, if we suspect that the feasible region is unbounded, then we could always add. So we'll do ax less or equal to b, E transpose x less or equal to big M, and x greater or equal to 0. So we add another constraint that the sum of the x's is less or equal to M, where M is a large number. Large enough. So large enough to include the optimal answer. All right. So we set it to a very large number. And this will make this set bounded. Okay. So that's that. That's this set. Now, the level set. Let's go to the level sets. Actually, I'm going to be more precise here. The set of theta such that f of theta z greater or equal to alpha, this set is bounded. Remember, when we do the alpha extension, we're going to maximize, we're going to choose the highest theta such that this is greater or equal to alpha cube. All right. So we want this set to be bounded, okay? And because we don't want the maximum to be plus infinity. Well, we could replace this x such that f of theta z greater or equal to alpha, and we could put a limit on you could put theta less or equal to big M, a big value M. All right. Now this set now, and then we do the maximum. Remember, at every iteration we do the maximum of theta, such as this. So now theta now is a finite number. It's not plus infinity. We made this. We made theta less or equal to some big large number. So now, if you go back to the proof, infinite convergence any M bigger than 1 will do. All the results that I go through, and if I choose any M, like M equal to 2, for example, then the proof of infinite conversion is still valid for minor modification. Okay. Now, for finite convergence, remember that delta F of Z star right, times delta of Z star is negative, right, for any infinite sequence. Remember that. Okay. So this implies that the set of theta such that F of theta Z star greater or equal to alpha star, this is just this is bounded. Why? Because this implies that this set here, this condition here, by quasi-concavity, I only need quasi-concavity, that F of gamma Z star is strictly negative, strictly less than F of Z star for gamma bigger than 1. I'm sorry, this should be delta Z star. This delta of Z star. All right. Because in the neighborhood, in the direction of delta Z star is descent direction. And therefore, it's going to imply that F of gamma Z star is less than F of delta Z star, which is equal to alpha star, right, for gamma bigger than 1. So therefore, the maximum is equal to 1 in this case. So this set is bounded. But remember, ZIQ converges to Z star over Q. And F is continuous. Okay? So therefore, this set theta such that F of theta delta of ZIQ greater or equal to alpha bar Q, this set here is obviously bounded. For Q large. Right? For one thing, alpha bar Q converges to alpha star, the function F is continuous, and the delta ZIQ converges to delta of Z star. I'm sorry, this is supposed to be delta of Z star. Okay, so in any case, my level set are bounded near the optimal solution. Okay, so I don't even need this constraint here. Okay, so this this assumption is not really a strong assumption. It's a weak assumption. We can always add this constraint here, and we should be okay. All right, now, how about the last strict local minimum? Okay. Now, before that, let's talk about continuously differentiable around X star. So I don't need differentiability everywhere. Okay, I need the to have finite convergence. I need the function to be differentiable on the neighborhood of every optimal vertex. Okay, so that's one. So and then we also need that X star to be a strict local minimum. If X star is an optimal solution, X star is strict local minimum. Well, so the assumption of strict local minimum okay, so let's assume that we're minimizing f of x subject to ax equal to b and x greater or equal to 0. All right, and let me assume that this set here is non-degenerate. All right, and A is M by N matrix. Okay, so what I'm going to do is I'm going to replace this function by another function, g of x. No, first of all, I'm going to call M is the minimum of xi subject to ax equal to b, x greater or equal to 0, and then xi basic. All right. So M is the smallest possible value that a basic variable can take. So this is strictly bigger than 0 because we're assuming non-degenerate of this set. Okay. So if I choose then, let's say little delta strictly less than M, and then I looked at g of x equal to f of x plus, I'm going to add the penalty term, so p times the sum of I equal 1 till n of the minimum of 1 and then xi over delta, all right, and then minus m times p. Okay, this function here. Now, if I have, so for a vertex, from the theory of linear programming, you can check my video on that. So that's of the form x beta plus a bar dot beta bar x beta bar equal to b bar, all right, and x beta bar greater or equal to 0. So beta is BFI, the basic feasible index. So the system like this, and then the vertex is just b bar and 0. In other words, x beta equal to b bar and x beta bar equal to 0. So the non-basic variable are set to 0, and the basic variable are equal to the right-hand side. And remember, here is non-degenerate, so b bar strictly positive. Every component of b bar is strictly positive. So as you can see that this term here, for the non-basic variable, is 0, so the minimum is 0. And for the basic variable, this term here is bigger than 1. All right, because remember, delta is strictly less than m, and this is less or equal to any basic variable. So this is bigger than 1, so the minimum is 1. So what this sum does, it counts how many basic variables we have. And in this instance, we have m. So we have p times m minus m times p. So that's 0. So therefore, from here then, for a vertex x, we have f of x equal to g of x. all right? For any vertex of this region. How about the other points? Well, the other point is if we are close to a vertex, let's say we have a V, so it's B bar minus A dot beta bar X beta bar, right? And this is X beta bar. So any point where X beta bar is almost zero. In other words, V is in the neighborhood of this vertex. Okay. So if we compute the sum here, this is too small, this is very small, so this is near B bar, and we already said that the minimum is going to be 1. So this term is going to be, for this variable, the sum will be m. So the Pm minus Pm is 0. But for the non-basic variable, x beta, they are non-zero, but they are almost 0. So the minimum is positive, okay? The minimum would be positive because we have extra terms. And therefore, g of x, g of v, is bigger than g of the vertex, b bar and 0. All right? For v near b bar and 0. So therefore, this problem here, P, I call this P, P then is equivalent to minimizing g of x subject to ax less or equal to b, x greater or equal to 0. So minimizing f or g will be the same thing. They are equivalent because they, at all the vertices, their value coincide, and outside the vertices, g takes on bigger value. So it cannot be the optimizer. So, and then, so the second thing, let's look at this function. So if this is, first of all, this term here, this is a concave function, okay? And this is concave, so the sum is concave. So g, if f is concave, g is also concave. And also, this function here is a piecewise linear function, all right? And at the vertices, it's a linear function in the neighborhood of that set. So therefore, it's differentiable also. If f is differentiable, this is also differentiable, okay? So we transform this problem into a problem where every vertex is a strict local minimum. Every optimal vertex is a strict local minimum with, of course, and we don't lose the differentiability around that vertex. Okay, so we looked at all the assumptions. So we are left with feasible set non-degenerate. How do we get around that? So why do we need this non-degeneracy of the feasible region? So B bar, so B is strictly positive. That implies that x equal to 0, right, is a vertex, of course. A vertex adjacent to n other vertices on the axis of Rn. So for example, in 2 dimension, so n equal to 2, right? My feasible region looks like this. So x equal to 0 is adjacent here to exactly 2 vertices. And that way, we chose this cone here. So C0 So we chose this cone as a starting cone. So this cone is a tight fit on the feasible region. This is my feasible region. Okay. So when one of the entries of B is 0, okay, that means my feasible region looks like this. So homogeneous equality. So my set looks probably like this. Okay. So the initial cone like this one here, is not a tight fit on the feasible region. Okay. So in other words, there are no feasible point along this axis. Okay. So I need to find this vector here. So let's say if I have this vector z, all right. So I could start with my C0 would be C of z, and this is 1, 0. I could start with z over E transpose z and 1, 0 in this instance. So it's no longer the cone defined by the basis of Rn, but it's this cone here. Now in higher dimension, so this is n equal to 2. In higher dimension, when B is not, when B is greater or equal to 0, right? Not strictly bigger than 0. So some BI's are 0. All right. Then x equal to 0 is adjacent to n or more vertices. Okay. That may not be on the axis. Okay. So we cannot use the starting cone, the starting cone. Let me give an example for n equal to 3. So this is our x equal to 0, and then this is okay. So my x equal to 0 is adjacent to v1, v2, v3, and v4. Okay. And some of these are not on the axis of Rn. So I cannot use this cone, starting cone. Right. But here I could say that I could start with my set of cone to be searched. I could start with C of v1, v2, v4, and the other one would be C of, let's say, v4, v2, v4, v3, v2, v4, and v3. Okay, I could set the cone to be searched are these two. Okay, in other words, like this cone here, and then this cone here. Okay, there is nothing special with starting only with one cone. We could start with two or many. All right, all the theorems still valid. Okay, so but the trick here, when we have this condition, we have some of the entries of BR0, we have to find all adjacent vertices. Okay. So it could be a simple case or it could be a complicated case. So that's why we use degeneracy. I mean, non-degenerate is not for the whole set, all right? But remember when we transform our initial program, we did phase one, okay? So we need the basic feasible solution obtained at the end of phase one. We need that to be non-degenerate, not the whole feasible region being non-degenerate, okay? So that's where this assumption is used. Let me now summarize about all these assumptions. That is, what is the largest set of problems that can be solved by this conical algorithm? First of all, we certainly need quasi-concavity, right? And we need continuity. Okay. And so that's for the infinite convergence. For finite convergence, we need differentiability. We need differentiability around optimal vertices. Okay, we need that. Now, strict local minimum, we saw how we can get over that, and everything else we can go over those assumptions. But also, remember, we needed that F is pseudo-concave not everywhere, but at optimal vertices. That is delta F of delta Z star times y minus delta of Z star. If this is less or equal to 0, that implies F of y less or equal to F of delta Z star. All right. We needed this to show that delta Z star was the unique optimizer of specific LP involving the gradient. Okay, so we needed that. So this is a pseudo-concavity property, but it's not needed everywhere. It's needed only at delta Z star, at the optimal answer, at every vertex. So we needed it. So this is the three minimal set, minimal assumption that will give us the largest set of problem that can be solved by the conical algorithm. So now this is the end of this series of video on concave minimization over polyhedral set. Please, if you have any comment or suggestion, send it to my email that it's at the beginning of each video.